Mark P. Otten back with you.
Okay, this is your introduction to the Bentler-Weeks Model, a way of organizing all of your equations that go into a structural equation model into one big fat matrix, and its size of the matrix depends on how many equations you have in there. And this kind of arose out of a need to just create a fundamental equation for this structural set of equations, structural equation model. There have been previous attempts at this. There's something called the LISREL model that came before the Bentler-Weeks model. This is Peter Bentler's attempt at simplifying a little bit how these are all written out. So in short, it's basically you have a bunch of equations and you make a list, and then you put them into matrices from there to organize and basically try to capture all of your equations and all of your possible equations in one swoop, so that this is flexible. You can have a bigger or smaller model, and this model will or this framework will expand or be reduced depending on the size of the model. So let's start with a new example. This is from Jody Ullman's chapter in Tabachnik and Feidel's book. We have a skiing example. Of course, if it's from Tabachnik and Feidel's book, a skiing example is sometimes quite common in that book. So we have, this is actually a very small, unrealistically small structural equation model. But it is a structural equation model. Why? Because we have at least one factor that is involved in a regression. Here we have two factors. So in circles there, we have love of skiing and ski trip satisfaction. Each of those might be measured multiple ways. In this case, love of skiing measured 2 ways. Ski trip satisfaction measured 2 ways. And then how much you love skiing is hypothesized as a predictor, or a something that leads to greater ski trip satisfaction. And then we also have an extra variable there, sensation seeking. So your setup for this is as follows. Treating our factor variable relationships as regressions, we can start writing out our equation. So let's do that for this model. Okay, so we can start by looking at our first dependent variable, v1 there, number of years skied. Basically, when we're writing out our equations, it's nice to just go dv by dv. So that first variable, v1, number of years skied, is being predicted by, or is part of the factor love of skiing. And so we start out with v1 as our dv, and then we're going to set that equal to star f1. What that means is the star is going to be a beta. This is, we're converting betas to stars just because that's what is standard form sometimes in SEM. That could have been a beta, but we're going to see those betas then organized into a matrix here in a minute. So I think the star is more convenient for the moment. And then we go plus E1. If you look at that variable up here in the top left, the E1 is out here on the end. That's the error value, equivalent in a regression to an intercept value. So that's all you have. And then this beta here, this factor loading, is labeled as a star. Same thing for V2, total number of days skied. The equation is going to look very similar, so we can go into the next line here. V2 equals star F1 plus E2, and usually the E's are then, like if it's a V1, it's an E1 that corresponds. If it's a V2, it's an E2. If it's suppose it's a V47, then you typically label the error as a 47 as well, just to keep it straight. So we've got those stars there to represent the factor loadings for each one. Then we can move on and write out similar equations for V3 and V4. V3, snow satisfaction. V4, food satisfaction. The two elements of ski trip satisfaction. I think if I were to go skiing, I think food satisfaction would probably rank higher for me, but that's okay. I'm not a skier. All right, so the only difference here is this 1. So as I mentioned when we were talking about, this was in the confirmatory factor analysis video, you have a choice when you set up your factors. You can either set one of the loadings to an initial value of 1 and then let the solution kind of iterate that loading so that you get a non-1 value in the end. Or you can set the variance of the factor itself to 1. So we have an example, one of each here. So on the left side here, we have love of skiing. The 1.00 here in the diagram represents the fact that the variance of that was set to 1. So what that does is basically just set the variance to 1. It's like creating a standardized variable, essentially. Standard deviation of love of skiing is 1, and it's going to fall on a normal curve scale and not be dependent on the units of the two components, number of years skied and total number of days skied. So we're sort of standardizing that variable up front. Doesn't really matter too much, typically, in my experience, doing one or the other here. So the other is on the right side here. We have a loading set to 1 initially, and what that does is it sets ski trip satisfaction to the units of snow satisfaction, which may be some sort of scale, like a Likert scale. And so then what that does is the factor then is on that same Likert scale that snow satisfaction is on. And then food satisfaction is free to vary around that scale. So anyway, for the purposes of our equations here, we have set a 1 as our factor loading. So when we set up V3 equals, we're not going to put a star, we're going to put 1 times F2 plus E3. So the 3 corresponds to V3, and the 1 corresponds to the loading for F2. And then for food satisfaction, we have a star again, or an asterisk as the loading there. So V4 equals star F2 plus E4. Okay, so these are our equations to represent our DVs 1, 2, 3, and 4. There are a couple of other things we need to note here. First of all, F2, ski trip satisfaction, is an IV, but it's also a DV, right? Because that's the beauty of SEM, is that we can have things predict other things, and then those things be predicted by new variables. So in this case, we have one factor predicting the other, love of skiing, predicting ski satisfaction. So we need to make an equation for F2, ski satisfaction. What are the IVs going to be in that equation? Well, we have sensation seeking here as an extra IV pointing to it. We have love of skiing here also, that's your factor 1. So we're going to have factor 1 and also variable 5 as your two IVs. And then this error out here on the end is going to be a D2 instead of an E. The D instead of an E is just notation for, okay, this is an error term that's associated with a factor as opposed to a measured variable, or a latent variable as opposed to a measured variable. So that's just notation. So let me see if I can write that out, if I can remember what I just said. F2 is our DV now. It's being predicted by F1, that's a star there. It's also being predicted by V5, so second star, and then you've got that D variable out in the end, and it's D2. We don't actually have a D1 because F1, the first factor, is not a dependent variable, so we're just skipping straight to D2, which is good actually because we're, like I said, it corresponds. So F2, the error term for that is going to be D2, so the D's or the number 2 matches in each one. Okay, so we pretty much are done. Like, we could stop here and just run an SEM, but what the experts have recommended over the years, including Peter Bentler, is to compile a list of all these equations and like I said at the beginning, make a framework, make a setup for this set of equations that's flexible enough to accommodate changes in your model, bigger and smaller models. There is a need to sort of define SEM in this way, in terms of a collection of equations that can then be collected together into one model, in this case the Bentler-Weeks Model, 1980. And like I mentioned also at the beginning of the video, there are a couple of different ways to do this. If you're going through this and you're like, oh, I would organize it differently this way, let me know if you have that idea or that notion, and we can talk about why. That level of skepticism is good. This is not the only way to organize these equations, but it is, if you believe it in the end, simpler than a couple of the ones that came before it, in particular the LISREL Lisserl model that came before it. Okay, so we're just basically compiling these regression equations into one list, and to do that we are switching from algebra to matrix algebra. So we're also switching from letters, English language letters, to Greek letters for the most part. And that's just how it goes, I guess, in statistics. Typically we have Greek letters that represent parameters that are then to be estimated by statistics. I don't know who invented that. Maybe Carl Pearson or somebody like that a long time ago decided that Greek letters would be useful. Anyway, we're carrying on the tradition here with the Bentler-Weeks model of doing that. So I'm going to list out these matrices in words here, and then we're going to see what they look like as part of our small sample example. And these probably will, without an example here, it might be kind of hard to conceptualize why there have to be 5 matrices as there are. But then we'll see it play out here in a second. So first of all, these first 2 matrices, eta and psi. That xi is pronounced psi, or I guess you could say it with a z, kind of sounds xi if you wanted. I don't know. I looked it up on how to pronounce it. If some of you guys might have experience with Greek life, and you might have seen these letters and tried to pronounce them before. But anyway, these 2 matrices are just the lists of DVs and lists of IVs. There are no numbers or regression coefficients of any kind, factor loadings, betas. Nothing goes in these matrices except lists of the variables. And we're separating out DVs and IVs because that's what we do in regression. The DVs tend to be predicted and the IVs tend to be the predictors. Then all of the betas or regression coefficients go into these matrices here. So we have a separate matrix for betas between dependent variables. Remember, a dependent variable can also be an independent variable in a different equation. That's the nature of SEM. So we have one matrix for those, and then another one for a matrix of betas between DVs and IVs. Those are the more traditional kind of equations where one variable just serves as either an IV or a DV and not both. So the first one is called beta, capital with a capital B there. That makes sense. It's a matrix of betas. But then we have another matrix of betas, and that one is called gamma. So I don't know. I would have probably named these like the first beta matrix and the second beta matrix, but maybe that got confusing when Peter was creating this model. I don't know. We could ask him. But anyway. We have the beta and gamma matrices, and those are filled with betas of various kinds. And then we have the last one here, which is actually outside of the framework there that you see at the top, that fundamental equation. This one is just a covariance matrix for the different IVs. So we need to state the relationships between the IVs as well as we're putting together the model. So let's see how this plays out in the small sample example. Okay, so here's what the Bentler-Weeks model looks like for our skiing example. We're going to start going left to right here and try to match up what this looks like in matrix form with what the equations that we wrote out look like. The first thing you might notice is that there are a lot of zeros in these matrices, and those are relationships that were not included in the model. So basically we are representing our set of equations with a framework that allows for more stuff than there actually is in there. So that's why it looks rather large, but actually when you look back at our equations, it's a relatively concise list. So the first thing going left to right is this eta matrix. And so if we look at our list here, the eta matrix is the matrix of dependent variables. And if we look at our equation list here, you just go down the list here, right? V1, V2, V3, V4, and F2, and those are your listed variables there. They also, once we convert them all to dependent variables as part of the eta matrix, we could rename them as eta 1, eta 2, and so on. And then if you do that, it sort of lumps together all your variables and your factors together as all alike in being etas. So anyway, that's just standard format. So we list our dependent variables going down, and then we do it again in the middle here. So as it says there at the beginning of the paragraph below, notice that eta is on both sides of the equation. This is because DVs can predict one another in SEM. So this just allows for that possibility. In between, we have the beta matrix. So let's go back and see what that was. The beta matrix is your matrix of betas between DVs. So these are relationships that exist between dependent variables in your data set. If there's no relationship there, it's going to be a 0 in the matrix. If there is something there, then it will be non-zero. And so what do we have? We have a 1 in the third row on the right side, the last column, and then a star. So what that is telling me is that we have, it's in the V3 row. So V3 may be related to something else that's also a DV. We go back here. What is V3 related to? V3 is related to F2. Aha. Okay. So V3 is related to F2. F2 is a DV, right? Because it was being predicted by F1. So that's what that relationship is representing, is the F2 V3 relationship. So we go back here, V3, it's in the V3 row, and then in the far right column, that's the fifth column in the beta matrix. Well, the fifth column is the F2 column. And the way you can figure that out is, well, there's 5 columns and 5 DVs, so you could go across. V1 is the first column, V2 second column, V3 first column, and so on. So then again, this 1 is your V3 F2 relationship, and in our list of equations, this is what it looked like. Now in the diagram, it looked like this one here. So the V3 F2 relationship, that was the one that we fixed to 1 to set the scale of the variable, or scale of the factor, to 1 to match snow satisfaction and ski trip satisfaction in scale. Okay, so that 1 there, that is what's listed here in the beta matrix. And then we have a star. You're dropping down to the V4 row for this one and staying in the F2 column, right? So the fourth row corresponds to V4. The fifth column in the beta matrix corresponds to F2, as we mentioned before. So this is V4 and F2. If we go to our list of equations, that's this one here, V4 and F2. And it's a star because it is an actual factor loading that we are starting out with a star here in measuring. So V3 and V4, in relating to F2, those are the two values that you see in the beta matrix. And there it is again. Everything else is 0. So what does that mean? That means that V1 is unrelated to all of their DVs, V2, V3, V4, etc. V2 is also unrelated to everything. V3 is unrelated to everything except F2. V4 unrelated to everything except F2, and so on. So it's so that beta matrix there is basically a really complicated looking representation of just the 1 and the star that represent your factor loadings, your initial values for factor loadings for V3 and V4 composing F2. All right. So the beta matrix complete, and also the eta matrix complete. We look now to the right, and we look at gamma, and we look at the other one, whose name I can never remember. That is your psi matrix. Thank you. I just talked about psi. Why couldn't I remember? Okay. So it's your matrix of IVs multiplied by your matrix of betas between DVs and IVs. So if we look at this as still an equation with the DVs out front here, it's a DV set of DVs that we're predicting. And then here we're looking at a matrix of relationships between those DVs and the independent variables, which are listed out here on the end. So let's go maybe row by row with this one as well. We have the first row, which is the V1 row. Again, these rows of this matrix are going to correspond to the 5 DVs going down, so there's 5 rows. And then there's going to be 6 columns. The 6 columns exist because there are 6 IVs. I'm sorry, 7 columns. There are 7 columns in the gamma matrix. I was like, wait a minute, there's 7 IVs. Okay, 7 columns, 7 IVs that exist here. So 5 rows for 5 DVs, 7 columns for 7 IVs. Okay, so that first row, the V1 row, has a 0 to start out. That's a 0 in the V1, V5 relationship. So we move on. V1, then here, in the second column, that's the V1, F1 relationship. We have a star. Okay, so let's go back and look at the diagram. That was V1, F1, and that is the star here representing the factor loading for love of skiing and number of years skied. And then we have a 1, so that's the V1, E1 relationship, and that is set to 1 initially. So V1 and E1, that's the the error that corresponds to V1. And there's a 1 there. We look at back at the equations that we listed out, V1 and E1, that we could put a 1 out here in front if we wanted. We could do that with each of our errors, actually. It's a little bit redundant to do that because 1 times that is just that. So I'm going to leave it actually out. But that's what the Bentler-Weeks model wants to see, is a 1 there, because that 1 represents that error. So again, V1, E1, the relationship there in the first row and third column is a 1. And so on. And you see some 1s coming down here. These are going to be your error values as they go along. So let's go through. So everything else is 0 in that first row, which means that V1 is unrelated to E2, E3, E4, and D2. Okay, so the second row, it's the V2 row, and V2 is unrelated to V5. Then the star here is F1, corresponding to F1. That's the F1 column. So V2 and F1 is a star. So let's look back at that. V2 and F1 is the factor loading for F1 and V2 there. So that is the star that you see in the second column. Then there's a 0 for V2 and E1, and then there's a 1 for V2 and E2. So that's part of the reason we label these as we do, is just to keep this straight. V2 and E2 correspond because they are, first of all, numbered the same, but also that's the error value that corresponds to that particular variable. So that's that 1 there. Everything else unrelated to V2. V3, well, V3 was already related to F2, but that was captured in the beta matrix. So not much is left for V3. V3 is the middle row here. Only 1 value exists. That is in the 5th column, a value of 1, and that is V3's relationship with E3, which is its error term there. Same thing for V4. V4 was already related to F2, captured in the beta matrix. So V4, everything is 0 except for its relationship with E4, similarly. Here in the second to last column, E4, V4, relationship of 1. Finally, we get to the last row of the gamma matrix. That is your F2 row, and we start out with 2 stars here. So what is happening with these 2 stars? F2 is related to V5 and F1. F2 is related to V5, sensation seeking, and F1, love of skiing. So that relationship there is actually a beta, or a factor loading. In this case, it's a beta. For each of your IVs, love of skiing and sensation seeking, F1 and V5, predicting F2 ski trip satisfaction. So those are your IV-DV relationships there. Then we have some zeros, and then finally at the end we have the last 1, and that 1 is F2 with D2. That is your error term for F2. All right, last but not least, we should not forget about the phi matrix. I don't know, maybe you want to call it the phi matrix. I think neither is incorrect. This is the variance-covariance matrix for the IV. So this is not going to be all that exciting to look at for our particular small sample example, but here it is. This matrix also, besides variances, it also captures any predicted correlations you might have between your variables. Here we had none of those. So basically all we have here is a bunch of variances, and one of them is fixed to 1. So that first top left here, by the way this is organized is you just list out your IVs going down the side, and then the same ones going across. So it's sort of the format of a correlation matrix, but just your IVs only. And so that top left value, that star, that is a variance for V5. What was V5? V5 was sensation seeking. So what happens when you add in an independent variable like sensation seeking is you have that relationship between it and ski trip satisfaction that was captured a minute ago as part of the Bentler-Weeks main model there. But then you also need to estimate or allow the model to estimate a variance for it. And so that's what that star here indicates. If, let's say, you wanted to also hypothesize something else about sensation seeking, suppose you wanted to say, well, I think sensation seeking is actually correlated with love of skiing, or maybe it predicts it. Well, if it was a prediction, it would go into the part of the Bentler-Weeks model that we just saw. That would be a relationship between an IV, and then it would turn that F1 value into a DV. So it would be an IV-DV relationship. But if we just called it a correlation, we're just like, well, they coexist. If you love skiing more, you seek out sensations and vice versa, right? If that were true, that would be a correlation, and then it would turn into a covariance, and it would go in V5F1, which would be right here. But here, we don't have that prediction, so we just leave that as a 0, and we leave a lot of zeros here on both top and bottom. By the way, this top and bottom of the equation, above and below the diagonal, should match, so it's a little bit redundant to say, okay, there's a 0 here for F1 with V5, and then there's also a 0 here for F1, V5 and F1 in reverse, same thing. So anyway, you can fill in a bunch of zeros. The one value that we have that's not a 0 here, this is F1's variance. That is the one that, if you go back to the model again, this one was set to 1 because we just decided to do that, and that set the scale of that particular factor to 1, the variance in particular to 1, and so that's why that looks like a 1 and not a star. The rest are stars. So for all of the error terms here, E1, the variance of that is a star. We're estimating that. We don't know it. We're not hypothesizing anything about it. Same thing for E2, E3, E4, on down to D2, which is the error term for F2. So again, if we had hypothesized correlations in here, we would have more. But for now, it's just a variance matrix with the variances down the diagonal and zeros everywhere else. Okay, so that was your quick, I don't know, that seemed like it was fast. You could rewind me, I guess, if you want on that. Going through what these matrices represent and how the Bentler-Weeks model is organized. What happens from here is typically we go into the math of what then is calculated for an SEM. I'm going to pause, though, because really the framework that's proposed here, the model matrices, are just a way, like I said, of organizing everything before you go forward. So that's what we have here, and later in the semester we'll contrast this with the Lisserl model a little bit more, and you'll see that this is actually relatively simple, believe it or not, compared to that one.